Hello everyone, welcome to the series of lectures on the course Foundations of Mathematics. This is the continuation of the part 2, Operations on Sets, and chapter name is Sets. See, what are disjoint sets? Supposing I have two sets with me, A and B, then these two sets A and B are said to be disjoint if their intersection is an empty set. That means they have no element in common. Okay. So two sets A and B are said to be disjoint if A intersection B is empty, that is, if A and B have no elements in common. For example, if you look at the first set, E is a set of all the even integers and O is the set of all odd integers. Okay, so given an integer, it cannot be both even as well as odd. So one integer cannot come in both these sets. So these two sets E and O are disjoint set because they have no element in common. All right. If you look at the second one, uh, a subset of R2 is given to you, collection of all the points x, y in R2 which satisfy this equation, and this is a straight line x plus y equal to 0, and B is set of all ordered pairs x, y such that x plus y is equal to 1. Okay, again a straight line. So these two are disjoint sets. Can you all imagine these two sets graphically? If you can do that, then you know the way you prove it will be very simple. So let me show you the graph of A and B on the xy plane. The line which is passing through the origin is your set A. Okay, so the line which is passing through the origin is your set A, and the line above is the set B. Okay, and you can see that they are parallel to each other and hence they will never meet. Okay, no matter where you go, how far you go, they are never going to meet. That means they have no points in common, right? And hence these two sets A and B which are given to me are disjoint sets. Okay, from the graph we got an idea that these two sets are disjoint sets, right? So now what I'll do, supposing there is a point in A and B, we'll assume that A intersection B is non-empty and we will arrive at a contradiction. Okay, so suppose A intersection B is non-empty. Because it is non-empty, there exists a point x comma y ordered pair in A intersection B. That means this point x comma y is there in A as well as B, right? So x comma y is there in A, and x comma y, this point is there in B as well. Now because it is there in A, it will satisfy the condition that x plus y equal to 0, and because it is in B, it will satisfy the condition x plus y equal to 1. That means x plus y equal to 0 and it is 1 also. That means 0 is equal to 1. That's a contradiction, right? Why we are getting this? Because we assume that A and B are not disjoint, and hence A and B are disjoint as we had seen in the graph. Okay, so these are disjoint sets. Next is difference of two sets. If I have two sets A and B, then the set difference of B from A is defined to be the set this. I will collect all the points in A which are not there in B. Okay, and it is written as A difference B. A this backslash B, and it is read as A difference B. Okay, and it is a collection of all the points in A which are not there in B. Okay, so this is a subset of A, but only of points from B you remove. Okay, I hope that's clear. That is, a point x will come in A difference B if and only if x is there in A and x is not there in B. So points which are there in A will come, but points which are there in B will not come. Okay, so here's the diagram. If I have the universal set as a rectangle and A and B are the two circles which you can see there, they are labeled as A and B. Then I'll take the set A Now from set A, I will remove all the points in B. So this gap which you can see in between here, those were the points which were common with A and B. So those points are removed, and finally what I have is all the points in A which are not in B. Okay, so this is difference A, difference B, difference of two sets. You can also similarly define the set B difference A. Okay, next, these are few exercises for you all. I want you all to go through all these exercises, okay, and let me know in the comments whether you all were able to do all these exercises or not. Okay, so let's quickly go through it. For the set A, what is A difference A? What is A difference B if A and B are disjoint? Okay, different possibilities are given. And the third says, what is A difference B if A is a subset of B? Okay, so try to answer these questions, simple ones. Then the second one says, if A, let A be the set of all n cross n real symmetric matrices and B be the set of all n cross n real skew symmetric matrices, then what is A difference B? So think over this, what is A difference B? The third one is this, all the ordered pairs x comma y such that mod x is less than 1. Okay, so what you can do is you can draw the you can first find the difference R2 difference A, and you can also draw the picture in R2 in xy plane. Okay, you can try to draw this picture R2 difference A. Okay, that's the difference of R2 and A. Fourth one, let A be the set of all n cross n real symmetric matrices and B be the set of all n cross n matrices. Now B is the set of any n cross n matrices. Then you describe the elements of the set A cross B. What kind of elements you are going to have in A difference B. Okay. And the last one says, for any sets A and B, you show that A union B, from A union B, if you remove A intersection B, that is same as you remove B from A, you remove A from B, and then you take their union. Okay, so you take a point on this side and you show that it is that side, and same thing you do for the converse. Okay, I hope this is clear. So do let me know in the comments whether you all are able to do this or not. Okay, next is symmetric difference. Supposing I have two sets A and B, then the symmetric difference of these two sets A and B is defined as A difference B union B difference A, and it is denoted by A delta B. So this is read as symmetric difference of A and B. And how it is defined? First, what you do, from A you remove all those points which are there in B, so you'll get A difference B, and then you take the set B and you remove all those points which are there in A from B, so you'll get this set, and then you take their union. Okay, if you see, we also have a different expression for this set from exercise number 5. Okay, so x will come in A delta B, that is symmetric difference of A and B, if it belongs to one of A and B but not both. Okay, can you all understand this? So a point x is coming in this set, that means it has to be in exactly one of the sets, either A or B. If it is there in both of them, it won't come, and if it is not there in any of them, then it won't come. Okay, so for a point to be in symmetric difference, it has to come in exactly one of A and B. So if you see the last exercise number 5 in the last slide, you will realize that symmetric difference A delta B can also be written as A union B difference A intersection B, because this expression here on the right hand side is same as this expression here on the right hand side. That's what exercise 5 is telling us. Alright, so if you want to draw the picture of this symmetric difference, this is how it is going to look. Okay, so intersection, you take the union first. Union is all this area of A and B, and from that you remove the intersection. So what is left here, this side and this side, that is symmetric difference of A and B. Alright, I hope that's clear. Now these are some exercises for you all based on symmetric difference, and intersection and union. Okay, so see that you all go through these exercises. Now, complement of a set. Now, whenever we talk about sets, supposing I am speaking about one set, then its elements are picked up from one set, which is the biggest known set to you. Okay, and that set is called the universal set, or sometimes it's also called the universe. So there is the biggest set which is possible that you can think of, that is the universal set, and you pick up elements from that set. Okay, so complement of a set is defined in this way. If A is a part of the universe U, okay, that is A is a subset of U, universal set is the biggest set and A is a small part of it, then the complement of A with respect to U I am talking about, the universal set, is written as A complement A and you write C on top, or sometimes we also write A dash. Okay, some books also use this, and it is defined to be all the elements in U which are not there in A. Okay, so A complement means everything which is there outside A. So you empty A, you remove all the points of A, and whatever is left out, that is A complement. Okay, so for example, if this is your universal set U, and this is the set A which I have, okay, then this what I'm shading here is the complement of A with respect to the universal set U. Okay, so it's very important to specify with respect to what you are taking the complement. So the shaded part is the complement of A with respect to the universal set U. Okay, so if A is a subset of S, then we call the set S difference A as the complement of A in S. Okay, so if you don't have the universal set say, and if you have a smaller set S, then we talk about complement of the set A in the set S with respect to the set S. Okay, so this is an example for you all. Some intervals are listed here, A, B, C. You'll have to compute their complements and what should be the universal set in each case. Okay, so that you all can think of. Okay, so I'll leave this as an exercise. Next is De Morgan's laws. You all must have already come across this in your 12th standard, but let me quickly go through it. This says for any two subsets A and B of the universal set, there's some universal set and A and B are subset of U. A intersection B complement is A complement union B complement, and A union B complement is A complement intersection B complement. Okay, so both these hold true. I will prove one of them, the other one you all can prove. Okay, and another thing that you all can try is try to draw the Venn diagrams, try to draw the pictures and get a feel of it. Okay, so in both the cases you all try to put it in the Venn diagrams. You put a Venn diagram for the left hand side, right hand side, and see that both give you the same area, same shaded region you should get from both the Venn diagrams. Okay, and same thing you can do for the second one as well. All right, so let's prove the first one. A intersection B complement is equal to A complement union B complement. So I will start with the point X in A intersection B complement. That means that point is not there in A intersection B, right? It's there in its complement, meaning it is not there in A intersection B. So X does not belong to A intersection B, which means X is not there in any of A and B. No, X is not there in at least one A or B, right? So X is not there in A or X is not there in B. This means X is there in A complement or X is there in B complement, which is same as writing X is there in A complement union B complement, and therefore A intersection B complement is contained in A complement union B complement. So one side is done, right? So again, if you try to look at the other way, that also goes in a similar way. So I will just leave it for you all. So see that you all go through the proof and try to understand and try to prove the second De Morgan's law also. Okay, and there's one more exercise for you. If A and B are subsets of R, then you try to show that these four statements are equivalent. Okay, how to show that the equivalent is already done in the first chapter. Okay, these are my references. Thank you.